Good morning. I'm going to try to explain how to go from a holomorphic one form of contact nu to a diffeomorphism, an analytic diffeomorphism, which only moves the term of order nu in the Puiseux expansion of a branch. Consider a branch gamma, the orange curve, whose irreducible Puiseux expansion is t to the power n, and the Puiseux expansion of the coordinate y, where we are assuming that m is greater than n. That means that y is tangent to the x-axis, so to y equals 0, gamma. Sorry. Now, this branch gamma has an implicit equation f, which we assume is irreducible, f. Because fxy equals 0 on gamma, this means that when substituting we get fxt yt equals 0. This subindex 0 will become apparent later, its meaning. And because this is 0, its derivative with respect to t is 0 also. So we get the most important equality in our computations, which is the fx, the partial of f with respect to x, on gamma times x dot plus fy on gamma times y dot equals 0. First relevant and crucial equality. Instead of working with f, well, once we have worked with f and its derivative, we can consider the dual form to f df, which is tangent to f equal constant, so it's tangent to gamma. Gamma is tangent to df, df has the expression fx dx plus fy di, but instead of working with the differential form, we take the vector field, the dual vector field. Consider x equals x dot equal minus fy, y dot equal fx, which is the dual vector field. If we take parametric initial conditions, x of 0 equal x0 t, y of 0 equal y0 t, that is the meaning of these subindices. They work as initial conditions for this vector field. If we take these initial conditions, then the solution is tangent to gamma. So gamma is invariant for this vector field. This does not mean that gamma is a set of fixed points. No, it means that gamma is just invariant. But that's what we need. Gamma is invariant for this vector field. And that's essentially the same thing as saying this. Yes, that's right. But we're going to need both things. Now, take the differential form omega. In order to simplify, let's assume, well, this must be, forget, unipotent, or whatever its name is, or nilpotent, or what you need. A belongs to xy to the maximal squared, and b belongs to whatever. Here conditions. Pull it back with omega, with gamma. So you get gamma star omega, which is just substituting x and y for x t and yt, zeros. This is x0 dot, 0, 0, y0 dot. Okay? This gives a tangency order, but we are not interested in this order, but in this one. We call it nu, which is the order you use, which the order of a of t plus b of t times y dot 0 over x dot 0. This is the same as divided by n t to the power n minus 1, as you do. Call it nu. This is the contact order of omega with gamma. And now, we want to know why you can remove the term of order nu from this Puiseux expansion without touching the previous ones. In order to do that, consider instead of omega, we take the dual vector field. Minus b partial x plus I partial y. So we consider this initial conditions problem. ICP, yeah. X dot equal minus b, y dot equal a on gamma. This Y is the set of red arrows on gamma. We are only interested on the behavior on gamma and near gamma. Okay. Now we have two vector fields, x and y. What we are going to do is study their difference, how they differ on gamma. Okay, we have y. Now, instead of x, and this is the silly trick which makes things very reasonable. Instead of x, which is just the differential of the implicit equation of gamma, we can multiply it times whatever we want as long as it is defined. So we multiply it times b over fy, the partial of f with respect to y. What happens with this? This vector field is perfectly defined on gamma because f is an irreducible equation of gamma, so its differential does not vanish on gamma. What happens with this vector field? Now, magically we get x dot equal minus b, and y dot equals b times fx over fy, which is not the same thing as a, obviously. But look at this. X dot equals minus b, x dot equal minus b, and now y dot, what's the relationship between these two things? Well, let's compute the error y commits when using it instead of this vector field. Let's subtract from this y. What do we get? Well, these are vectors, so we can compute their differences. These are vectors on each point, we can compute their differences. The difference on the x coordinate is 0, and the difference on the y coordinate is this expression, but on gamma, which is the only place we're interested on gamma, this, because of this, becomes at minus bt times y dot over x dot. This is the key thing. This equality is the same as this equality. When substituting here, we get this equality, which is exactly of order nu. So, the error of y with respect to an invariant, a vector field which leaves gamma invariant is of order t to the power nu. We have a vector field x, or if you want, now b over fy x, which leaves gamma invariant. These are the green arrows, and we have another vector field y which does not leave gamma invariant, but which incurs an error of order exactly t to the power nu on gamma. So, if you move gamma, how to draw this? If you move gamma, plup, this is gamma, sigma y, excuse me, sigma y, this is the vector field, and this is the differential isomorphism associated to the vector field. If you move gamma by y, what you are moving the terms of order t to the power nu and further on, but not before. This is what this says. This is the error. Okay, in order to prove this precisely, you have to reparameterize everything and be careful with all the conditions. It is important that omega is nilpotent, etc., etc. But in the end, what you get is, what's the solution of this differential equation? X e of t minus b times s plus s squared whatever, y c of t plus a of t times s plus s squared whatever, because omega is nilpotent, blah, 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 blah. You can reparameterize everything and get this. The new equation for a parameter s is of the form u to the power n. So you have the first part is the same, essentially, with a different name. And y ts is of the form, this is not t, sorry, excuse me, this is y, obviously. I've mistaken t for y everywhere here. And y of us is, these terms are constant because of this. You cannot move things of less order if your error is of greater order. So these terms remain constant, and then the first time a non-constant term appears is in a linear fashion. This is k. K is a parameter which depends exactly on the form omega. This is the first term times, excuse me, this is u times s, u to the power nu. Now notice that s is what gives you the diffeomorphism. You compute the exponential up to a value s. K, there's something here which is, this is a nu plus, sorry about that. My mistake, excuse me. The first terms are constant. Then you get your term of order nu plus a linear thing, k times s, u to the power nu, plus whatever, of order s squared, and in u of order greater than nu. So you have a linear diffeomorphism here, which depends on s. You choose the s you need in order to make this 0. That s gives you the diffeomorphism, which annihilates the term of order nu. Actually, this k plus s, etc., depends on this form, but only on the, this will be alpha t to the power nu plus whatever, only on this alpha. And obviously it depends also on n, because you are going to compute an nth root here, but it's easy to compute. The only things that influence this value are the linear parts appearing here, the linear terms, the terms of order 1 in S, and the terms of order nu, but it's essentially easy to compute. Now, sorry about this mess in the end, but what we do is you have your vector field given by df, the vector field given by omega, the contact order, and the contact order gives exactly the error incurred by y when using it instead of x on gamma. So y does not leave gamma invariant, but only incurs an error of order t to the power nu on the y coordinate. This implies that you can leave the x coordinate constant, t to the power n, u to the power n, and get the second coordinate. The first parameters are fixed, ay, and then only the parameter of order nu can be eliminated, and the following ones are whatever. We are not interested in those right now. I hope this clarifies more or less my paper on the Revista Matemática Iberoamericana for the Felipe conference in 2017, I think. And my paper with Javier Ribon in the Canadian Journal of Mathematics. This is much longer, and it's much more related to blow-ups, which do not appear in this reasoning, but they are geometrically interesting. Well, thank you for your attention. I hope this helps understand my works here. And just a comment on when you have not a branch but several branches, what you do is exactly the same thing, but yes, you take the same thing, the reducible equation. It's very important that the equation is irreducible. Consider the tangent vector field, and now this is what I think should work. I'm not sure it works because I haven't worked with multiple branches ever, but I think it should work. You take the omega, but you don't have an order. If I recall correctly, I'm going to erase this. What you do is to work essentially with a list of orders, nu gamma 1, omega, nu gamma k of omega. And I do not recall precisely what you do, but I think you take the infimum of this or something similar. These values are ordered in the same way as the branches are ordered in your brackets. And there are the families here. What happens is, as long as you have this list, and you take an infimum or whatever, you are choosing one branch in which to move or on which to move the term nu sub gamma r of omega. I think this reasoning should work exactly the same. Instead of tangent to gamma, you have tangent to gamma I. And if you take an infimum here, somehow, if you move gamma I, that infimum, you are not moving the previous ones on the other branches. This is what I think should work. I haven't written it in detail, but we can do it if you want. Or I can try to, if you want. But what I wanted to do in this video is just explain my computation for a single branch and to tell you, well, I think this generalizes, but I'm not sure, obviously. Thank you very much.